Now let us go through a few examples of differential equations and direction fields. So let me first try to figure out what we can tell from the direction field without even knowing what the differential equation is. So notice that we can kind of, when we follow arrows like this, what we get is solutions of this differential equation. And I think it's pretty clear that if you do this, then all solutions are going to be increasing functions. So the reason to this is because if you look carefully at these arrows, then all of them point a little bit upwards. I mean, all these arrows, they point to the right rather than to the left, and then upward rather than downwards, in the sense that in all these arrows, both x and y components are positive. So these arrows, kind of like this, or maybe like this, or maybe like this, but in any case, both the first coordinate and the second coordinate of the arrow of these vectors are positive. So of course, it means that all solutions of this differential equation are going to be increasing functions. All solutions are, I will write like this, increasing functions. Well, but notice that you can also tell it from the original differential equation, because the right hand side is the sum of two squares, and the square is of course always non-negative, so the right hand side is non-negative. But if a y prime is non-negative, then y itself is an increasing function. Yeah, and well, of course you can verify it. If say you want to go to this online direction field plot, then you can play with solutions a little bit and see how they follow the arrows, and that all of them are indeed increasing functions. Okay, now let me look at the second example. And again, suppose that we haven't seen the differential equation, so we're just looking at the direction field. And from the direction field, we can see that solutions that live here, they are decreasing functions, and they approach negative 1/2. So solutions that live here, they are increasing functions, and they approach negative 1/2 too. And solutions that are here in this part, they are increasing functions, yeah, and they approach infinity, right? So let me write that solutions here, solutions are increasing, here solutions are decreasing, and here solutions are increasing, which we can see by these arrows pointing a little bit downward or a little bit upward, meaning that the y component of the vector is positive or negative. But of course, at the same time, we can look at this differential equation, right? And then we can think, so under which condition is the right-hand side is negative, and under which condition is it positive? And so let us think of ln y squared plus 3. So plus 3/4. So when is it positive? When is it negative? And when is it 0? So when is it positive? When is it 0? And when is it negative? Well, this depends on whether y squared plus 3/4 is bigger than 1, equals 1, or less than 1. Right? So in other words, whether y squared is bigger than 1/4, equals 1/4, or less than 1/4. And then the equation y squared equals 1/4 has two solutions, minus half and plus half, and then if this is minus 1/2 and this is 1/2, then if y is less than negative 1/2, then y squared plus 3/4 is positive, between minus half and 1/2 negative, and here positive. Sorry, yeah, the ln of it is positive. So that's how we know that the right-hand side of our differential equation is positive or negative. But if the right-hand side of our differential equation is positive, it means that all functions are increasing. So if y of 0 is bigger than 1/2, then y is increasing, and we can see that at the same time it approaches infinity. So if y of 0 is between negative 1/2 and 1/2, then y is decreasing, and it is decreasing towards negative 1/2. This is what we see from the picture, negative 1/2. Alright, so and if y of 0 is less than negative 1/2, then y is increasing, and it is increasing towards negative 1/2. So the limit of y of t as t goes to infinity is negative 1/2 if y of 0 is less than 1/2. Okay, this is similar. So notice that this example, it has the same component, ln of y squared plus 3/4, plus it has this component, which is it depends on t, but it is always non-negative. And the differential equation is a little bit more complicated. Well, and the direction field is a little bit more complicated, but still we have the same basic structure. So there is an equilibrium solution at positive 1/2, an equilibrium solution at negative 1/2, and all other solutions, they approach this solution when t goes to infinity. Well, if the initial point is below 1/2. Well, if the initial point is above 1/2, then, well, it seems to still approach infinity, well, only probably slower than as it does in the previous example, but the behavior is similar. So let me maybe do this 1 plus cosine of 3t times log square plus 3/4. So here is our example. So if probably we want the behavior for more values of t, say, let's do t from -20 to 20. Oops, sorry. Yeah, this is what's going on here. So it still approaches the same, well, depending on the initial condition, it approaches either negative 1/2 or infinity, well, only at different pace. Well, let's look at this equation. So now this is still the product of two components, but now notice that this cosine of 3t does not have a constant sign. So it's not positive anymore. So it may be positive, maybe negative, depending on t. So which means that, well, imagine if we have a solution of this differential equation, and if its behavior is determined by the function ln of y squared plus 3/4, if in the two slides ago, if it was supposed to be decreasing, then now as t is increasing, sometimes cosine is positive, sometimes negative, so it's not going to decrease anymore, but rather is going to decrease or increase, and which is what we see here. So it's kind of oscillating behavior. Right, so what we see here is that we still have the same two equilibrium solutions, but the rest of the solutions, they're oscillating. And of course we can try to do it here. This is our tool, and so this is between minus 1/2 and plus 1/2. This is exactly 1/2. This is above 1/2, below 1/2. So all of them are oscillating. All right. Let us look at this example. There are two things that I would like to pay your attention to. So first of all, let's notice that the right-hand side t minus y is, well, is 0 if t equals y. Right? And when the right-hand side of the differential equation is 0, well, it means that the direction field is, its first component is 1, and its second component is 0. Right? So the first component 1, second 0, so the vector 1, 0 is a horizontal vector. So it is a vector that points exactly to the right. Which we can see here. Right? So the line y equals t is this one. And along this line, you see that all vectors are exactly horizontal. Well, at the same time, the right-hand side is, of course, positive if if y is bigger than t, and negative if y is less than t. Right, so the region where y is less than t is above this triangle. So here y is less than t. Here y is less than t. So therefore the right-hand side of our differential equation is negative, which you can see by all arrows pointing a little bit downward. So the second component of all these vectors is negative, strictly negative. So which means that within this area, all solutions are decreasing. So all solutions are decreasing. But then in this area, we have the opposite picture. Right? So in this area, y is bigger than t. So y prime is positive. And here, all solutions are increasing. Well, but it is actually a little bit more complicated. Right? So let me erase this. and show you another feature of this very interesting differential equation. And so what I want to show is that if you look at this line, then all these arrows, they are exactly at 45 degrees, and all these arrows, they belong to the same line. Y equals t minus 1. This means that y equals t minus 1 is a solution. Of this differential equation. But even more interesting is that if you look at other solutions of this differential equation, then you will see that other solutions, they approach this solution. So all other solutions, as t goes to infinity, they approach the solution y equals t minus 1. So this means that the general solution of this differential equation looks like t minus 1 plus some constant times, well, some specific function. Well, let me denote it as maybe g of t, while this g of t approaches 0 as t approaches infinity. Well, most of the time, but of course not all the time, but usually it means that this is really t minus 1 plus c times e to the power minus t. Usually. I mean, of course, since I designed this vector field, I know that it's true, but it could be probably or plus c times e to the minus 2t, or could be probably times c times something more complicated. But anyway, it should be a term that approaches 0 if t goes to infinity. So this is what we conclude by just looking at the direction field. So we can identify regions of the ty plane where solutions are increasing, regions where they are decreasing, and then in this case we see that there is a particular nice solution that we can immediately identify too, and then by the fact that all other solutions they approach it, we can conclude that the general solution of this differential equation is of some specific form. All right, so here is kind of a similar example. It is a bit more complicated, but the main idea is the same. So let me show it to you. So if you look at it carefully, you will see that there is also this linear solution. So all these arrows, they are on the same line, so which means that y equals t. This is a solution. But it is actually more than that, because you can also see that there exist other solutions, and they kind of approach this as t goes to infinity and as t goes to negative infinity, right? So not only y equals t is a solution, but other solutions, they approach y equals t both on when t goes to plus infinity and to minus infinity, right? So which means that the general solution looks like y equals t plus, well, something that contains a parameter c. So I'll write with c, and this something with constant c, it has this property that it approaches 0 as t approaches plus or minus infinity. So which means that it could be something like y equals t plus c times, say, e to the minus t square, or t plus c times 1 over 1 plus t square, or something like that. I know, well, since I created this equation on purpose, of course I know that this is in fact the second option, but of course we cannot conclude it by just staring at the picture. But we can see that the general solution has the structure that there is a particular solution, y equals t, and that all other solutions, they